Hello, everybody. Greetings, everyone. Hey, welcome to Galaxy Land. This is chapter 13 right here. We're going to talk about normal galaxies and active galaxies. Normals are like the Milky Way, and active galaxies are galaxies that are in the process of going crazy in one way or the other. This one that you're looking at right here on the screen is one of the most famous ones. It's called Centaurus A. It's relatively close, so we wouldn't be able to see it this well. And it has the features of what looks like here an elliptical galaxy right here. And this is what you see in spiral galaxies, big dust lanes. And we can tell it's dust because it's obscuring the material behind it. Anyway, you don't see these two together. And so this sounds like the big C, collisions. This is an example of a galaxy that has collided with another galaxy. This is when you get all sorts of interesting effects. This thing is spewing out huge amounts of radio energy in the radio part of the spectrum. That's unusual for normal galaxies and a variety of other things. So let's move on here. Here's the Hubble classification of galaxies. If you notice, Hubble's name keeps popping up. The guy basically dominated the first half of the 20th century in astronomy because he had access to all the big telescopes. First at Mount Wilson, just north of Los Angeles, and then Mount Palomar in the middle of the 20th century. So he was responsible for a lot of stuff. You're going to see one super important thing. There are three types of galaxies: the so-called ellipticals, the spirals, the normals, the barred spirals, and then the third type is the irregulars. Let's take the easiest ones first. The ellipticals come in a variety of shapes, from sort of circular to sort of like a football to something that's skinnier than that. And the number basically tells you what shape it is. Now notice these stars don't have any blue stars in them. They also don't have any gas and dust. So since they don't have any blue stars, they're not young, because blue stars are generally less than 10 million years old. And no gas and dust means that no star birth has occurred in these galaxies for probably something like 8 or 10 billion years. That's a long time to have no action. But that's what happens if you're an elliptical. Now, the normal spirals have spiral arms. You've seen what that looks like. And these things, this classification scheme has to do with the size of the nucleus, gets smaller from A to C. And also the arms are more tightly wound from A to C and more loosely wound when you get to C. Notice the normals don't have any bars. The barred ones do. Our galaxy, remember, is a barred spiral, and other than that, the nucleus size and the tightness of winding of the spiral arms is just like in the normal spirals above. Here's the irregulars, and you guessed it, the irregulars they're irregular, friends, and they don't have any patterns. They're galaxies that have clearly been messed with and came out number 2 out of 2. They've had collisions that didn't go well. And so the question is, can these types of galaxies can you make a spiral into an elliptical? And the answer is yes, you could. You'd have to destroy you'd have to consume most of the gas and dust, which is in the disks. That's where all these blue stars are. But the nucleus of the spirals look a lot like the ellipticals, and so that's been food for thought. And no doubt collisions have had a big part in this whole thing. Now, I thought it'd be fun for you to see. We talked about Cepheids in the Milky Way. That was easy, but when you do Cepheids in distant galaxies, it's not easy. This is way out at M100, which is, I'm guessing, like 50 million light years away. And here's what they actually look like. And you can see the dates on these images and how they change brightness. Notice that this one's getting a little dimmer, and then it's beginning to come back. That's how you actually measure these things. And that's what happened when Hubble and his folks started finding Cepheids in other galaxies, not just in globular clusters in the Milky Way, but in other galaxies. That changed the world because it showed these other galaxies really were other galaxies, and they were far away. They weren't just part of the Milky Way. Here it is. This is momentous back in the 20s when it was created because it changed the whole universe. It said, look, if we plot the velocity of a galaxy moving away from us, the velocity of a galaxy moving away from us versus the distance of the galaxy, we get this interesting straight line. Boy, that's wild. It means that the galaxies that are farthest away are moving away fastest, and the galaxies that are closest are moving away slowest, okay? But they're all moving away, and this is taken now as the first real observational evidence of the large-scale expansion of the universe. The large-scale expansion of the universe. And this was huge because this argued very strongly in favor of what became known as the Big Bang, which was the time about 14 billion years ago, when time, space, matter, and energy appeared and all began moving rapidly away from each other. That's called the large-scale expansion. We still see that sort of memorialized in the galaxies as we look at them out into deep space. Now, this is something I picked up. This is about dark matter. I showed you a velocity rotation curve here. We've got orbital speed over here on the left side, orbital speed. This is for other galaxies. Here we got 4 separate galaxies, NGC 4378 all down to 7664. If you're wondering what the NGC stands for, it stands for New General Catalog, but it's not new anymore, but it's still called NGC. And these are just 4 galaxies that happen to be in it. And they actually plotted how fast stars appeared to be orbiting around the center versus their distance, exactly like we did for the Milky Way before. And you remember, we were expecting to see a Kepler path down here, which indicated that the galaxies had a star-like entity at the center around which everything was orbiting. But none of them do. They all look like our galaxy. They have flat signatures out to the edge. And this proves that very well, it indicates, this is strong evidence, put it that way, that all other galaxies, in effect, are surrounded by large envelopes of dark matter. Remember, we don't know what dark matter is. We simply know that it's invisible and that it's got gravity. And you're seeing it in other galaxies. It's assumed to be in all galaxies, so obviously we haven't observed all of them yet. There are a few galaxies nowadays that have been found that don't have dark matter. That gets everybody frothed up because it's exciting to find something that seems to be different. Supermassive black holes are in most galaxies. They tend to go from 4 million solar masses down to a billion, or up to a billion. And the second thing is that dark matter is a persistent feature in almost all galaxies. And so supermassive black holes were around before the galaxies, and dark matter was around before the galaxies. So they're playing big roles in the origin of these things, which is just being worked out now. Here's the local group. Now, galaxies are found in groups, or clusters, if you will. They're rarely found alone. This one is not very spectacular, but it's ours. So we call it local. It only has like 5 dozen galaxies in it. The big spectacular ones have thousands, but you know, we're small potatoes. Here's our galaxy, the Milky Way. And here's Andromeda. Beautiful galaxy, very Milky Way-like. Here's Triangulum, also a spiral galaxy. Those are the only 3 spirals in this whole local group. The rest of them are, I'm blocking it out with my rectangle, I'm sorry, but the rest of them are what are called ellipticals. I showed you that before. Those are really bizarre galaxies that have nothing happening into them. They're basically dormant. And also irregulars. Now, irregulars are believed to be the result of collisions. Okay, now that we got that off our chest, that suggests that it's been a lot of galaxy colliding in this local group. And the 3 winners are obvious: the Milky Way, Andromeda, and Triangulum. The irony of this is that in a few billion years, these 3 will be spare parts as well, because they're all going to undergo bad collisions. I'm not sure what that means. Now, I thought this was fun because this shows you an example of how galaxies collide, and this shows you a computer simulation of it. And this particular galaxy is one you've seen before. This is the whirlpool. This is the symbol of our home page on Canvas for this course. If you look closely, you'll recognize it. Now, the way it's believed to have begun is the bigger galaxy just happened to have a close encounter with the small one. Notice they were well behaved prior to that time, no problems. And notice when you start, oh, I should tell you that when galaxies collide, usually the stars do not bounce off each other like that. The stars are so far apart compared to their size that they completely miss each other. They just kind of go through each other. But what does impact is the gravity fields of the stars are already pulling on the stars in the larger galaxy, and the little galaxies really get the worst of it. The little galaxies always get roughed up in these kind of competitions. Notice that even the big galaxy is starting to form spiral arms here. This is one theory for the origin of spiral arms. And guess what happens to this poor cute little guy here? The big guy is basically taking a good share of his gas and dust. Not stars so much, but gas and dust really gets stripped. And that goes into the nucleus where the supermassive black holes are, which is an interesting topic too. But anyways, you can see that the simulation is able to reproduce the basic features of the two galaxies, including the tail between them, and the formation of spiral arms in both of them, which is interesting. Now, let's talk about active galactic nuclei. This is a famous type called Seyferts. They were discovered in the early 40s. People had no idea what these things were back in those days. The one distinguishing characteristic is what you see here, a very bright nucleus. And that was very, very hard to explain because the amount of energy coming out of the nucleus alone, now we're talking only the nucleus, was about the same as the amount of energy coming out from all the stars in the rest of the galaxy. Now that's hard to explain. That suggests that there's no way you can do that kind of energy production with just stars in the nucleus. So that suggests that there was something else going on, but believe me, in the 40s and 50s and 60s, they did not know what was going on at all. The nukes alone are as bright as the entire regular galaxies, and so forth. These things are seen today in the universe. There you can actually see one. You can see the spiral arms and everything, and all the bright stars forming in them. But these things have these very, very bright nuclei, which got everybody's attention. Now, the big enchilada here was discovered in the 60s. They're called quasars. You're looking at space telescope pictures, Hubble Space Telescope pictures of them. And this was the first time anybody could see that, in fact, the quasars are actually embedded in galaxies. But the quasars are so bright, they completely dominate the galaxy. Before the space telescope, ground-based telescopes could not resolve this galactic structure. So they thought maybe these things are just floating around by themselves, but they are simply like the Seyferts, only bigger and better. The nuclei of the quasars does not just equal the energy output of the stars, it increases it by 100 to 1,000 times. And so they knew they had a big problem. How do we explain this huge energy production that we see in all the quasars? But it's easier now that we know that they're in galaxies as opposed to just floating around. Here's the model for what's going on. Supermassive black holes with an accretion disk. Here's the supermassive black hole. You can take a look at this in the PowerPoint yourself and see it in more detail. And swirling around it is this accretion disk, which is mostly hydrogen gas, some dust, mainly stars that have been muscled by this thing, just torn apart. The bigger these accretion disks get, by the way, don't confuse accretion disk with planetary accretion, not related. In the planetary accretion, you're building planets. In these things, everything is being torn apart. What happens is the tidal forces of the supermassive black holes pretty much disassembles anything and then sucks it thoroughly into the event horizon of the black hole, where it disappears. And so eventually, if you wait long enough, it's like a slow vacuum cleaner. These things all spiral in, and all of a sudden you're starting to clean up your accretion disk. Now, here's the quasar summary. The nuclei are 100 plus to 1,000 times as bright as the stars in a regular galaxy. This model that I showed you works for quasars and Seyferts. Now, the interesting thing about the quasars, this is a big hint too, they're only seen at large redshifts, and that means they're very far away, very far away. Now, the quasar epoch in the universe was apparently 10 billion years ago. That means there were a lot of quasars in the universe 10 billion years ago, but there don't seem to be any now. We see them as sort of remnants of themselves, only very far away. So, for example, if you had a quasar that was 10 billion light years away, it would take the light 10 billion years to get here, and during that time, the quasar might have somehow disappeared, but we would still see the light coming from that great distance away. And that's basically what's happening. The large accretion disks are full of gas dust and stars. As I said, these were discovered in the